Hello, everyone. Welcome to Convex Optimization. This is lecture 14. Can you guys hear me well? All right. So can anyone guess what my background is? Where my background is today? So I promise you like a world tour, like every week. Yeah, pretty good guess. Japan looks like Japan. In fact, this is not actually Japan. Instead, this is Wuhan University in China, at the central China in the city called Wuhan. And Wuhan also happens to be the city where the novel coronavirus first starts. And the people of the city suffered tremendously due to the slow responses of the local government and prevention effort, and then later also suffered again from the very ruthless lockdown rule that lasted for months. So now it's a spring season. It's a typical season for people of Wuhan to come to Wuhan University's campus to enjoy the cherry blossom. Like it's really beautiful out there. I wish I can go someday. But in this situation, they all will have the same fate as we do here, working from home and staying at home, and then only seeing the cherry blossom from remotely over the cloud. So yeah, it's a city that's devastated by the pandemic, and I hope the world has learned the lesson. So in the future that a similar situation will be controlled better. All right. Now we are seeing more people joining the call. So let's get the lecture started. So again, this is lecture 14. So I guess people should be able to see my writings on the board. All right, so this is lecture 14. So this is the second lecture where we start after we started to talk about the online learning part of the class. So today we're going to be talking about the first general algorithm for online convex optimization. Okay, so online gradient descent, projected gradient descent. You see a lot of similarity of this algorithm with the gradient descent and stochastic gradient descent that we learned previously, but the settings slightly different, and the proof of how this algorithm works is also going to be different. In particular, remember last time we talked about the problem of learning from expert advice, and at the very end we generalized the setting a little bit to cover like optimization over the sequence of adversarially chosen convex function and minimize regret. So let's state the setting again as a quick review, and then we'll give examples. We'll give several examples to motivate the study of this problem called online convex optimization, so that I can convince you this is a problem that's worth studying. Okay, and then we'll state the algorithm, online gradient descent, and then analyze its properties. All right. So that's a plan for today's lecture. So we'll start with a setting of online convex optimization. So in online convex optimization, the goal is to minimize regret. So we define regret as a time horizon t is a property of the algorithm or the learner, the policy that the learner runs. Okay, so I will say this algorithm to be A. Okay, so the regret is defined to be the sequence of loss that this is the sequences losses that this learner has incurred by playing say strategy xt, by playing action xt at every iteration. So this action can be a point in a convex set. What are we comparing to? We're just like in optimization, we're comparing to the optimal solution. So in this case, like maybe we don't really have an optimal solution, so we can compare to any point. So we can compare to to any fixed point in the hindsight. Okay, so t from 1 to t. Like so this can be this can work for any u, in which case we can parameterize this regret by u. But alternatively, we can also, I guess, just choose u to be the minimizer. We can choose u to be the one that minimizes this sequences of function subject to an additional constraint. Okay, so K is a convex set. So this is a convex set. Okay, so notice that this regret is often an upper bound that we derive. So depending on what the sequences of convex functions that we receive, f1 to ft, then we get different regrets. So in terms of analyzing that algorithm and coming up with a performance guarantee of the algorithm, we're taking the worst case perspective. So we wanted to design an algorithm that minimizes the worst case regret. So in some sense, we're taking the soup over all sequences of convex functions. Like I guess each one of them is in some family of convex functions. So we've talked about a lot of family of convex functions. We talked about functions that are just convex and Lipschitz. We talk about functions that are Lipschitz and smooth, functions that are twice differentiable, functions that are like Hessian Lipschitz and satisfy other fancier and more restrictive properties, and then work out their computational guarantee. So the same story goes here. So we're also going to be talking about different family of convex functions, like in our study of this regret minimization problem. Okay, let's more formally state the setting. So the setting is like a game, right? So you have a player and you have an adversary. So the player declares that the hearsay algorithm A that she's going to be using throughout the game, which takes into account of all the transcript of the entire play up to this point, and then decide what the next XT is going to be like. Okay, and the adversary, based on this algorithm A, will choose F1, F2 to Ft. Okay, the adversary will choose a sequence of convex functions from this set of F. Okay, and the game start at time equals to 1 and then continue since this is repeated game, and it goes like so follows. The player plays xt xk from a given convex set K using algorithm A. Okay, and then the player incur loss of ft xt. After incurring the loss, the player receives some feedback from nature. Okay, and there could be various kinds of feedbacks. So so suppose the player receives a gradient. Okay, gradient of ft xt. So we call this a full information setting. It will be clear, like once we get to examples, why this is called the full information. Okay, and then like sometimes we don't get to see the gradient, but instead we only see the function evaluation. Okay, so this would correspond to zeroth order optimization problem. The first one would correspond to first order optimization problem. And in the online learning literature, this is also often called the player sees a banded feedback. This is full information feedback. Okay, there's a third type that's less studied, but I think it's worthwhile that we spell it out. So sometimes the player actually get his hand on the full function, so ft as a function. Okay, in which case the player, after receiving a ft, can potentially evaluate the gradient at other points than xt and evaluate the function value and other points other than the points that you played before seeing ft. Okay, so I call this, I guess, like I guess full function access. Yeah, so the difference between full function accesses and full information feedback are often not great. So for online convex optimization problems, so that's the reason why like often having access to the gradient itself is already sufficient for us to think about how to solve this problem. Okay, so let's like maybe give a few examples to instantiate this setting and this regret minimization problem appropriately, and also build intuition. Okay, so the first example that we're going to have is the example that we had from last time, just as a review, learning from expert advice. Okay, so recalling this setting, so there are a bag of like a panel of experts who offer advices on stocks to buy, so or offer advices on whether a stock would go up or go down, and you have to choose among them without knowing that which one is the actual expert, which one is going to make less mistakes, and so on. And at the end of the day, you want to keep playing this game and then do as well as the best expert in the hindsight, like throughout the game. Okay, so the way that we can frame this problem in the online convex optimization setting is to instantiate what these FTs are, what this convex set K are, and what are these sequences of functions, and also your choices of which expert to take. Okay? So let's say so K is the convex set. It's a decision space. So in some sense, your decision is to maybe randomly pick, potentially randomly pick any one of the experts and follow their advice. So I guess the convex function K is simply the probability simplex. Let's say that there are n experts, so you will have the probability simplex smaller than 1. Okay, so this defines the probability simplex. Let's call it sigma n. Okay, now what is the sequences of functions that the loss functions that we're trying to minimize? So it's simply f of x being a linear function, so L of t x. So notice that this is related to the generalization of learning from expert advice that we've seen previously, while this LT is not just 0 and 1, right? It's not a 0-1 vector. It can be anything that's bounded between 0 and 1. And then we've talked about the hedge algorithm that can actually achieve logarithmic dependence on n, and the learning bound that has lower graph, right? So so this L is every coordinate of this L corresponds to the loss that you incur if you pick that expert. And so this inner product is equal to sum of 1 to n x I multiply with LT. So this is a loss of the bag of expert at time t for each one of them. And by definition, this is just the expectation of if you choose your action by the distribution given by x and taking expectation over this randomness, and then Li A. Okay. So what is the kind of feedback that we that we get in this model. Okay, suppose it is a full information feedback, then what we end up getting is a gradient of this function f(t) of x at every iteration. Okay, so this makes sense in the stock market when you are a relatively small player and your actions is not really changing the market. And then after every days of taking actions and trading and making decisions, you can look at all your answers in the hindsight by looking at suppose you didn't pick this stock. What if you picked the other one? And suppose you decided to hold rather than to sell, what your gain is for today, right? So you can evaluate like what if I followed the advice of the other expert rather than the expert that I picked, right? You can learn from that kind of feedback for all experts in the back. So in that case, you do receive the full information. Full feedback will be the gradient of f(t) of x, and that will be simply L of t, right? So notice that in this case, the full information feedback has no difference to the full function axis. Okay, so that's one instance where it makes sense to think about why like observing the gradient at this particular location is actually all of the information that's available to you. On the other hand, like sometimes if you are a big players, or like if it takes you like some amount of money, and if any single day you can only get the advice from one of the experts rather than all of them, right? So in that case, all you can observe is the feedback that corresponding to your choice, right? So you can only see I guess E of A, where E is a standard basis that gives you LT of A. Okay, so in this case, you are only observing the objective function value of the action that you played. In this case, it becomes the banded feedback. Okay, so the historical reason why this is called a bandit model comes from gambling and slot machines. So in casinos, you have like 10 slot machines over there, and different one of them, each one of them has a different expected return, right? So without knowing like which slot machine is gonna like spit out the most rewards if you keep pulling it, like there's no way that you can figure this out by asking the owner of the casino. Instead, like the bandit algorithm would predict, or the bandit algorithm will try to learn by trial and error and to balance exploitation and exploration, so that at the end of the day you can do as well as knowing which slot machine is the best at the very beginning. Okay, so that's bandits. And it's called multi-arm bandits because those slot machines typically look like in the old days, the slot machine look like people who's a bandit wearing having a gun on one side and having only one arm on the other side, and you can pull that one arm again and again and again, right? So so it's I guess a bad naming. It doesn't directly reveal the nature of the problem, which is really like zero-order optimization in the online setting. But for historical reasons, people are calling this bandit feedback, right? And in this case, the learning from expert advice with bandit feedback is essentially like the adversarial bandit setting, where the casino can be rigged, and the casino can even change like which slot machine is the best, like after every step, and depending on your choices of which machine that you prefer. Okay. So second example. So let's maybe talk about an example that's statistical in nature. Okay, so statisticians love linear models. So we use linear models for doing like for doing predictions for say linear regression to predict continuous responses, and we use linear logistic regression to determine like positive negative outcomes of treatment and so on. But what if we don't really know about the world, and what we don't know where the data is coming from? Like, how can we still guarantee that? And then also, what if we don't even have the IID assumption that the data is coming from? And can we come up with an algorithm that allow us to do the best predictions that linear models are able to offer without making strong assumptions about how the world works? Okay, so online online linear models. Like sometimes these are called generalized linear models. Okay, so so what is the space that you can choose your decision? So these are the space of the coefficients. So using the notation from this optimization literature, we use X so rather than theta. Okay. So xt is in this decision space, which is often the subset of R to the n. Okay, so this is at every time step, you pick one particular coefficient vector and use it to do prediction. And then the feature that you observe in every iteration is say phi of t. Okay, so this is also a subset of R to the n. So this feature can be used to measure the situation right now, can be used to measure the personalized information about the patient before the doctor's deciding which treatment to use. And what's the loss function that we want to minimize? So in linear regression, this ft x is simply x phi of t. So this is how your linear model is going to predict, minus yt. Okay, and this is the observed label that's revealed to you in the hindsight, like after you've played X. Okay, so maybe like you don't want the properties of this ordinarily square kind of formula. You don't like square loss. You can change it to say the absolute value, right? In which case you get the max absolute deviation. Or you can use the Hoover function to interpolate between these two, so you can get the smoothness and the robustness at the same time, right? So you get Hoover function x minus yt, absolute value. Okay. So maybe suppose you have a classification problem, and then you can do the logistic loss, which we've seen several times already in this course. So which is a function of the score function and then your eventual binary label. Suppose you have multiple multiple classes, and you can do cross entropy and so on. So the linear model is really the cornerstone of like, and the changing these loss functions, and most of these loss functions are convex, are really the cornerstone of modern machine learning and statistics. And often, like, just to come up with a new loss function like for your specific problem would leads to a paper that's highly cited and highly appreciated in a particular subfield. Okay, so what kind of feedback that people are getting? Okay, so in this case, if we talk about online linear model, then this is saying that at every iteration, we're getting like a new data point. So we get xt at the time of prediction, sorry, we get the phi t at the time of prediction, and then we get yt and phi t together as a feedback, right? So what does it mean? Like, this means that we actually have a full function access, And also we can use this to construct the corresponding gradient of this function ft, right? Because say in the linear regression case, the gradient of ft at xt is a function of phi and yt for sure. So we get phi, so this gives you the vector multiply with multiply with your choice of xt, vt minus yt, okay, minus the residual, multiply with the residual. Yeah, so for other generalized linear model, what's being changed is basically how you measure the difference between your square function and yt, and nothing else. And suppose there's an algorithm that minimizes regret. That means that like we don't have to know whether the data is drawn IID from any distribution, and then we are able to compete with the best linear predictors in the hindsight. And if like my algorithm that runs online linear models isn't really giving you a good prediction, it is a problem with a linear function class, not a problem with my algorithm not finding the not finding the best linear predictor within the class. So yeah, let me know if there are any questions that comes to mind, and then just stop me at any point during the lecture, right? So let's give another example. Example 3, I guess online shortest path. Okay, online shortest path. Maybe let's come up with a concrete example here. So say that many of you are graduate students of UCSB, so chances are at least a big subset of you are staying in your dorm rooms in San Clemente Village. Okay, so this is where you live. Okay, so every single day, like maybe you can cook yourself, but for some of you who don't really cook, you have to get food somewhere. And during the social distancing period and during the lockdown, you have to try to minimize your encountering with other people out there, especially that you're staying in Isla Vista, right? So getting to your favorite restaurant can be pretty challenging, and they are so you want to get from where you live to say your favorite restaurant. Okay. So how do you get there? So there are multiple paths that you can take to get there. There are traffic junctions that given by these nodes of a graph. Okay. And then there are different ways that you can take to get from one point to another. Okay, so this is a starting point. This is a final point, source and the sink, source and terminal. On every edge, if you decide to take that edge, and then take that path, and then there is a chance that you run into someone who's contracted with you're suspicious of anyone who's not wearing a mask who carries the coronavirus. Okay, so there are edge weights that's assigned at every single day. There are potentially different edge weights that's assigned with every edge here, which measures the likelihood of running into someone who may pass you the virus. Okay, so there are some edge weights. Let's maybe measure it by cost. So cost, say cost 1, cost 2, cost 2, cost 3, and so on. So in total, you have a cost vector that's in R to the number of edges of this graph. Okay, so so suppose all these costs are known to you. then it will be a trivial problem of running of solving the linear program of max flow, right? So that you can maximize your cumulative you can minimize your cumulative cost subject to the constraint, or like rather it's simply the shortest path, right? But what happens is that these people move around like all day long. Like each time you go out, you don't really know like what these cost vectors are at this particular point in time, at this particular day. Okay, so can you can you come up with a strategy that minimizes your chances of getting the coronavirus without knowing how the world works? Okay. So maybe you can only like observe people once you have decided to take one particular path from S to T. Also, that's the only feedback that you can get from one trip to your favorite restaurant. Okay, so let's maybe formulate this problem as an optimization problem and as an online convex optimization problem. So let's say we have this decision variable xt in R to the e. Okay, so this xt needs to be positive, and then xt also needs to satisfy some kind of constraint. So since we want to minimize the cumulative cost of every single time, so this xt is I guess your chance of taking one particular path when you are at the junction. So you are at every single day, right? So it doesn't have to sum to 1 because you need to take multiple passes to get from S to T. But this xt measures the probability over your decision of taking a particular edge as you get from S to T. So there are also a set of constraints, right? So first of all, like you have to come out. So since these are probabilities, then xt of I j and sum over j when I is equal to sync sum over I all j and ij is the subset of the edges needs to be equal to 1. So you have to go out, otherwise you won't get your lunch. And secondly, so sum over I j is equal to t, and I j is in the set of edges xt ij needs to be 1 because ultimately you want to get to your restaurant. Okay, and the third constraint is saying that on every intermediate node that the flow that goes in and the flow that goes out should be the same. So so with this much probability that you get to this this node, and then like you have to get out, you can't stay there forever. Okay, so this is saying that for xt of I j, I guess iv sum over I when iv is in the set of edges. So this is equal to sum of xt vj I sum over j and vj in the set of edges e, they need to be equal, and this needs to hold for all the in edges except the source and terminal. Okay, so far we've only written like affine equality constraints, and clearly this is feasible if there exists at least one path from S to T. And the intersection of intersections of hyperplanes are clearly carving out a convex set, right? And in addition, In addition, since these are choices, for T, we need this to hold for all T, right? So this means that at every single day, we're getting the same same convex set. So all of these will give us this convex set K that we're optimizing over. Okay, and what are these? So these are the sum of linear functions, and linear functions are convex functions. So this defines the sequences of Ft. So how about the feedback model? It really depends on how you look at it. Suppose you look at Google Map, and then there's a way that Google Map is measuring this cost for every single day, if for those paths, even if you haven't taken those passes. Okay, at the end of the day, like Google is going to report the aggregate statistics of every street, and then like you have full information feedback because you can reconstruct what actually happened for today, and then then to answer the counterfactual question. So what if I've taken a different path? What's my likelihood of getting the virus? Okay, but it could also be a bandit problem. So suppose you take your path and then can only observe like on the way from San Clemente village to Lawang, like you can only observe the cost of the edges that you have visited. So then that will be a bandit problem. Okay. So so I give one last example before we get to the algorithm. So the last example that I give is portfolio optimization. Okay, so so previously, like we talked about the learning from expert advice, where the experts are predicting the ups and downs of a single stock, right? But in practice, nobody is just gonna buy one single stock and stock and hope that it's gonna work. Instead, all your financial expert would advise you to diversify your portfolio so that you hold not just the tech stock, but also other stocks that can be used to hedge against the ups and downs of the tech sector, so that at the end of the day, you can maximize your so-called risk-adjusted return, right? So how do we solve this problem technically? So let's like using maybe online convex optimization. So let's define like the daily return of a bunch of stocks. Okay, so let's say that in every day we observe a vector of relative ratio of up and down. So that's the returns of a stock. So this, say you have n stocks, this RT is in R to the n, satisfying this RT larger than 0. So what is RT? Let me give you an example. Say for stock I, RTI, stock I, the corresponding relative ratio of stock I is measured by RT. And for example, if Apple stock is like $100 today, and then it dropped to 95 at the end of the day, dropped 95 tomorrow, then RT corresponding to Apple would be like 95 divided by 100. Okay, so that's why it's always a non-negative value. So even if it gets to 0, like that means that you've lost everything, right? So I guess there are exceptions. Like in the most recent case, the oil price, the future of the oil price is actually negative for some reason, but yeah, so let's not worry about those cases right now. Okay, so what is your decision? So out of the n stocks, your decision that you're going to be making every day is to somehow allocate your to allocate the amount of money that you are willing to invest into proportions. So what proportion of my money I wanted to invest to Tesla, which proportion I wanted to invest to Apple, and so on. So this decision will be an XT, and clearly XT is a probability vector that's in the probability simplex of dimension n. Okay, and now how do we measure the return? So suppose you have a unit 1 at every day. So after you hold it for a day, then based on the relative ratio, what you end up getting is actually just a linear function of RT and XT. Okay, so RT, the inner product for RT and XT, measures like the relative measures the relative amount of money that you have like after trading this for 1 day. Okay, so but this is multiplicative. So after trading for T days, so the cumulative amount, suppose you start with day 1 with a asset of 1, then T from 1 to T, this will give you the cumulative relative gain. This is not a problem that can be studied under online convex optimization, because we've been looking at only loss functions that add up rather than taking the product, right? So maybe let's take log to make it in the logarithmic scale. So in this case, we get a log transformation of this, and then we get the sum of T from 1 to T and log of each individual day, RT and XT. So can anyone tell me like what these individual functions are? So this log RT transpose XT, is it convex or is it concave? So notice that X is non-negative and RT is also non-negative. So the log like is well defined. Anyone? Is log convex or concave? I wanted to make sure that I'm not talking into a void. Like you guys can really hear me. Okay, good. Okay, so log is a concave function. So we have a sequences of concave functions that we wanted to maximize, right? So this is a cumulative gain rather than cumulative losses, right? So we can define the f t of xt to be negative log of RT transpose XT, which recovers the online convex optimization setting. Okay, and in terms of the regret, let's try to make sense of it. So the regret would be negative log RT XT minus I guess plus the max of X in probability simplex and sum of log RTX. So what is this? This is the best fixed proportion investment strategy in the hindsight. Okay, so notice that this is a log transformation of the total return. Like suppose you know like which fixed proportion of your asset to allocate to each stock at the very beginning, and then this is what you will end up getting. Okay, so notice that this doesn't mean that you don't have to buy or sell at all. But instead, at every single day, you have to somehow rebalance such that if you pick like to invest all stocks with 1/n, right? With 1/n of your money, then depending on the ups and downs of this stock, then that means the relative proportion of the money that your asset represents will have to change, and you need to somehow rebalance that every day, right? So if you ignore just the trading cost of doing that, and this like online convex optimization algorithm is going to provide something that if you keep playing this forever, and then you will do as well as the best fixed proportion investment in the hindsight. So this is your log of your return. Okay, cumulative return. So I hope these examples convince you that this is an interesting and useful setting, because all these application scenarios, in all these application scenarios, we're not really making any assumptions about how the world works. So stock market, they're financial math people who use stochastic calculus to model the and mostly differential equations to model how the stock market would go up and down, leading to mostly like no free lunch theorems. You can model the market, and there are other ways of modeling that with pure statistics by making strong assumptions on the stationarity and IID, assumptions on the return. There are game theoretic studies that tries to model people's behavior and people's greed, so as to exploit the market inefficiency. So all those are super interesting. But like as computer scientists, like we don't really want to make any of those assumptions because we don't know which one of those assumptions would stand. And this style of like assuming the worst and then trying to do the best is the philosophy that's behind a lot of the algorithmic design in computer science and economics. So in particular, the famous algorithm from information theorist in Stanford, Thomas Cover, developed an algorithm called the universal portfolio that essentially tries to achieve no regret on this problem. I think it's 1994. Yeah, I can't remember exactly, but do look up. This guy like is no longer teaching, and he's now like I guess believes that his algorithm would work with some extensions, and he's now I think running his own hedge fund. Okay, so I hope this example tells us that online convex optimization is useful, and it is particularly useful in places where we don't have a good model of the world. So now let's talk about the first algorithm that we can use to generally solve a family of online convex optimization problem. So the algorithm is like intuitive and you've seen it before. Okay, so this is called online gradient descent, OGD. Okay, and we'll consider instead of the banded feedback, let's consider the full information feedback. So we will receive a subgradient. In every iteration. So this can be thought of as a full information feedback. Okay. So it works like the follows. So you have input before the game starts. So the convex set of all the available actions to you are given, and you are also told that the game is going to last for capital T iterations. And well, like in order to invoke OGD, you have to come up with a sequences of step sizes. Okay. Okay. So now for T from 1 to T, you basically play your, yeah, I guess you also need an initialization x1, right? You need x1. But without loss of generality, you can pick x1 to be just 0. Okay, so at the beginning, you play xt and then observe the subgradient of this function at your chosen xt. And then you update using the projected subgradient descent, basically, which is a two-step process. You first update it to some intermediate value using the learning rate that's specified a priori, gt, and then xt plus 1 is equal to projection to this given convex set t of xt plus. Okay, that would be the OGD algorithm. Simple, right? So we're going to be analyzing the regret of OGD under a set of familiar assumptions. So we assume that the sequences of functions are all G Lipschitz, which says that for any x and y, fx minus fy is smaller than G times the norm of xy. So standard definition of Lipschitzness of a function. So this doesn't require f to be this doesn't require f to be differentiable. So in particular, it handles, say, the absolute value function. So or like maybe the entire set of subdifferential at any x. This is any x, y smaller than g. Okay, so of course this function needs to be convex. Otherwise, sometimes even the subdifferential is not defined. And lastly, we want to make an assumption of a convex set. So convex set K obeys that the diameter of this convex set K is smaller than D. So what does this mean? This means that for any x, y in K, then the distance of x, y measured in two norms is smaller than D. So if this convex set K is a norm ball, then this simply is given by 2 times the radius of that norm ball, right? So it's something that you used to measure, like what is the longest line segments that you can fit into a convex set. Okay, so these are the 3 assumptions that we make about the problem. And then let me state the theorem, and then we're gonna go to the break. Okay, so the theorem says that if you take the learning rate eta t to be the diameter over the Lipschitz constant and square root of t for t equals to 1, 2, 3, all the way to t, and then the regret is equal to t from 1 to t ft. So this is a definition of the regret, right? So the regret of this algorithm are in fact, let's not deal with, so for any u in this set K, smaller than 2/3 of g d square root of t. So notice that this choice of learning rate is independent to t. So we don't actually, to run OGD, we don't actually have to know what the horizon is. So that means that this is so-called anytime algorithm, that we can run it, and for every time like we look back, and then it always satisfies this regret bound for all t simultaneously. So for all capital T simultaneously. Okay, and also we can compare to any fixed comparator U in the convex set, which include choosing this to be the U that minimizes the minimizes the sum of losses in the hindsight. Okay, and the last thing to observe about this is the parts about this theorem is that it's proportional to square root of t, which means that as t gets larger, the average regret per iteration actually goes to 0 as a function of 1 over square root of t. So this means that this is a no regret algorithm like for this general family of problem. So we'll take a break of 5 minutes and we'll resume at 2:04. Okay. Meanwhile, post your questions and comments in a Zoom group chat. See you guys in a little bit. All right. It's 4 minutes past 2, so let's resume the lecture. All right, so we're going to be proving this theorem on the regret bound for the online gradient descent. Okay, so to start with, let's like make use of our assumptions that each one of these FTs are convex function. So by by far, like this first order condition for convexity should be pretty straightforward to you. So that it's like you can think about it from the Taylor series of expansion. You can also think about the local linearization is always lower bound in the function. So let's linearize the function at xt, and that always serves as a lower bound at any other point. So let's take that other point to be x star. So we'll get this gt, which is subgradient at f of f at xt, x star minus xt. Okay, so this is by convex. So notice that if we just move things around, we can use it to recover the suboptimality gap, right? So we have x t minus f t. Okay, so so in this proof, I'm just going to be using x star, but notice that you can replace x star with any other point, right? So that follows from the convexity of f. And this is lower bounded by gt and xt minus x star. Okay, now so remember that this is tricks that we used in proving the convergence of gradient descent. So that involves working out the square of the Euclidean distances of your current iterate, and then try to bound the next iterate with the current iterate, and then apply the update rule of the algorithm. So we're going to do the same here. So by the OGD algorithm, so this is a projected subgradient descent. So that will be the projection to convex at k xt minus eta t gt minus x star. Okay, and notice that this x star is always in the in the feasible region k. So by the non-expansiveness of projection operator, projection, you always get closer to any points that's in the space, right? So you can upper bound this by simply dropping this projection. So that gives you xt minus eta t gt minus x star. So we've covered all these techniques in our analysis of the gradient descent and subgradient methods and stochastic subgradient methods multiple times. I'm just covering this in details again and again so that you actually pick up like these techniques, so you can think of them like when you are running into these problems yourself. Okay, so let's now expand this square terms into I guess quadratic terms, and then into cross terms. So first of all, at the beginning, we said that we want to upper bound this using the previous rounds of the distance between this two between this point xt to x star. So now we were able to construct it, and now the other quadratic term would be eta t square gt square. Okay, and now we have the cross term, which looks like eta t gt inner product with xt minus x star, right? So everything just follows through naturally. So notice that we can now move we can move this to the other side of the inequality, and then make use of the lower bound of this, so that we can construct an upper bound of the final goal that we try to achieve. So let's do that. Let's apply the implication of convexity, and then obtain our iterate after moving this to the other side. So let's multiply this by a factor of 2. Okay, multiply this by a factor of 2. So we get 2 times ft xt minus ft x star smaller than 2 times gt inner product with xt minus x star. Okay, since we move this to the other side and move this to the other side and divide both sides by eta t, so we can upper bound this with I guess once we move this to the other side and then divide both sides by eta t, then we get xt minus x star square, and then we'll move this term to the right hand side, minus xt plus 1 minus x star square plus eta t square gt square, and divide everything by eta t, right? So so that would be simply this, and then we can drop this square term here. So notice that now we have something that more or less telescopes. And if we use our previous approach, we would move eta t to the left-hand side, and then use that simple bound of minimum multiply with the sum to control it. But now let's do it in a slightly different way, so that we can obtain a slightly better bound for the chosen sequences of learning rate that we picked in the theorem. Okay, let's start a new page. So I'll rewrite it. Don't worry, I'll rewrite the last iterate. So the last iterate will be ftxt minus ft x star smaller than 1 over eta t xt minus x star minus xt minus 1 this t plus 1 minus x star square plus eta t g t square. So let's there's a factor of 2 here. Let's add everything together. Okay, let's add everything together, and on the left hand side we obtain the regret. The 2 times the regret. This is defined to be 2 times the sum of ft xt minus ft x star. Okay, on the right hand side, first of all we have sum of eta t, and then by our assumption that that function f are all Lipschitz, and the subgradient is upper bounded by g, so that we can replace this with the sum of t multiply with g squared. Okay, for the first term, we can we can shift things a bit. So it looks like eta t and then so it doesn't directly cancel out, but it almost cancels out. It almost cancels out in a sense that we can group all the terms and group all the coefficients of terms with the same t. Okay, and that gives us sum of t from 1 to t, 1 over eta t minus 1 over eta t minus 1. Okay, so notice that at t equals 1, eta t minus 1 is not really well defined, but let's abuse notation for now and then write it down like this. So we have x t minus x star square. And after all these, we're going to subtract the last part, which is x t capital T plus 1 minus x star. Okay, and that's multiplied with eta t, 1 over eta t, plus sum of eta t g squared. So notice that this is negative, so we can drop it, and we define eta t minus 1. I guess eta t zeros when t is chosen to be 1 to be just positive infinity, right? So then everything's the same as the previous line. So now let's apply the diameter. Since both xt and x star, so they are feasible solutions, let's apply the diameter condition. So this is one of the 3 assumptions that we made. So this is smaller than d square sum of t from 1 to t, 1 over eta t minus 1 over eta t minus 1. So now this eta t starts to cancel out, right? So now we really have the telescoping sum where eta starts to cancel out. And what this is going to give us is d square of only the last one. Right? So that will give us only the last one, because everything else would cancel out. 1 over eta capital T plus the sum of eta t from 1 to t. Okay, so we're now left with the summations. So let's recall that how is eta t defined. So eta t in our main theorem is defined to be d over g square root of t. Right? So let's substitute this into the equation. We get d g square root of t. Okay. On the second term, we have g square of multiply with d, g, these two got canceled, and then we are left with sum of t from 1 to t, 1 over square root of t. Okay, so what is this 1 plus 1 over square root of 2 plus 1 over square root of 3 plus all the way to 1 over square root of t. Can anyone give me an upper bound of this series as a function of the capital T? Yeah, clearly this is lower bounded by t times 1 over square root of t equal to square root of t, but how about an upper bound? Yeah, this is pretty elementary. So the typical trick that we've learned from the say high school mathematics course is to maybe like upper bound this series with the integral, so it becomes easier to calculate, right? So the sum of I from 1 to t, 1 over square root of I. So I argue that this is smaller than the integral from 0 to t 1 over square root of x dx. So why is that the case? So we have this integral, and the sum is in fact just always smaller than the integral pointwise. Therefore, like calculating the integral exactly would give an upper bound of this quantity. So by this calculus, this becomes 2 square root of x t 0, and this gives us 2 times square root of t. Okay, so in other words, we have an upper bound of this that's 2 times square root of t, and a lower bound of square root of t. So it is really bounded in between like two constants on the order of square root of t. Okay, so now that we have this calculation, and then we can upper bound this with dg yeah, sorry. So there was a small typo that nobody has caught up on. So square root of t is on the numerator rather than the denominator, plus 2 times dg square root of t, and then the final result is obtained by dividing both sides of this inequality by a factor of 2. Okay, so finally we get the regret is smaller than 1.5 dg square root of t. Okay, so so this can actually be improved. Suppose we use a fixed learning rate and know the horizon t ahead of time. So suppose we take eta t just to be a fixed quantity of d g square root of t throughout, rather than using the decaying learning rate of d over g square root of small t, right? Suppose we use a constant learning rate, then we can plug in everything and then get the right we can plug in everything and get the right calculation, and we'll end up getting the regret of the same dg square root of t, but the second term will no longer have that factor of 2. So you end up getting you end up getting I guess simply dg square root of t, which means that you can improve this constant from 1.5 to 1. Like suppose you know know the capital T ahead of time. Okay. So before I move to the strongly convex case, are there any questions about the proof? Because I've explained every step, and everything should be straightforward to you now that you've seen the convergence proof from the gradient methods and subgradient methods. Okay, let's move on to talk about the strongly convex case. So in addition to what we assumed previously, so let's in addition assume that Ft is M strongly convex. Okay, so still we wanted to assume that Ft is G Lipschitz. So yeah, in this case, we actually don't need the boundedness of the domain. Okay, so like we've used the D doesn't have to be bounded. So in the strongly convex case, the theorem for OGD obeys that the regret is smaller than g squared over 2m and 1 plus log t. So instead of having regret that that depends on square root of t, in the general case, if the sequences of functions are strongly convex, then we can get a regret bound that's only logarithmic in horizon. So that's a very significant improvement over the over the previous case. Okay, we'll see how that is connected to the convergence rate of strongly convex case, like after we've proved this theorem. Okay. This is improved from something that's order square root of t. So let's prove this. So again, the first thing that we use is by convexity. Actually by the m strong convexity of function ft, we can get a slightly stronger bond comparing to the one that we used previously. So notice that the bond that we used previously is ft xt minus ft x star smaller than 2 gt transpose xt minus x star. So this is the bond that we had previously. So now, in addition to that, we have we have this term. We can bond this with by subtracting another quadratic function from this upper bound. Okay, so this is a new thing. So let's call this inequality inequality 1. Okay. So now in the second step, let's follow the same steps by bounding the distance of your current iterate to your reference point x star. So this is again projection xt minus beta t gt by the definition of the algorithm. And by the non-expansiveness of the projection operator, we have xt minus eta t gt minus x star. Okay. Now we can now we can do the same trick by expanding this quadratic function, right? We can expand this quadratic function, which gives us c minus x star minus eta t star gt plus eta t star gt square minus 2 times eta t gt transpose xt minus x star. Okay, and we can move this again to the other side, and that gives us the same bound that we had before. Gt xt minus x star is smaller than that's 2 times this is smaller than xt minus x star square minus xt plus 1 minus x star square by simply moving this to the right hand side and then divide both sides by eta t. You get eta t and gt square. So let's apply the upper bound of g Lipschitzness of the function ft to get rid of the to get rid of this dependence on GT, so we can obtain an upper bound like that. So let's call this inequality 2. Okay, by combine 1 and 2, then we get a bound of the suboptimality of xt on this function ft in terms of everything that's on the right hand side of 2. And then sum up over t from 1 to t. Okay, so let's so we've done the calculation. That's exactly the same as the one that we had in the previous page. So we are able to recover the regrets, 2 times the regret on the left hand side, and we get that this is smaller than now that we plug in this and also move this new part to the right hand side, which gives us well, so let's maybe write it out with more details. Minus x star minus xt plus 1 minus x star. Okay, we had this, but we also have something. We also have something more. We have something more that's coming from that's coming from this part, right? So minus m, right? So and lastly, we have a g squared sum of I from 1 to t eta t. Okay, so now let's combine the coefficients of xt minus x star squared. Let's combine the coefficients and then work with this part. So we can write this as the sum from t from 1 to t. Then recall previously we had 1 over eta t minus 1 over eta t minus 1. Yeah, 1 minus t minus 1. And now minus m x star minus xt square. And in addition, there's a negative term that we ignore, which is 1 over eta t xt plus 1 minus x star. So this is the term that we don't care about. This part is smaller than 0. So now we are left with this. So what is our choice of the learning rate? So actually I didn't I forgot to state this in the theorem. So let's add that. Choosing eta t to be 1 over m times t. Okay. Assume ft is m strongly convex. Okay. So with this, we can substitute this eta t into this equation. Yeah, we can substitute this into this equation. We get t from 1 to t m times t. So this is, since this is 1 over eta t minus m times t minus 1 minus m. What is this? So can someone give me the calculation of this leading coefficient? Just a quick answer, either unmute yourself or write in the group chat. Excellent. So this cancels out and you get 0. And all you're left with is the last term, g square, of the sum of this over the t iterates. So that will give you, that will be, so we are choosing this to be 1 over mt. So let's extract the 1 over m here. So we have 1 plus 1 over 2 plus 1 over 3 plus 1 over t. Okay. So we are left with another like series sum. So what's the for people who still remember this, like what do we get with the sum of 1 over t when t from 1 adds from 1 to capital T? What do we get here? What is the scale of the sum of 1 over t? These are harmonic series, and we've used it multiple times when analyzing the convergence of the subgradient methods. We've talked about series sums being summable or not summable. So clearly, as t goes to infinity, this goes to infinity. So this is not summable, but it grows very slowly. Who still remembers this from, say, lecture 3? Yeah, excellent, Kaichi. So you can upper bound the harmonic series with something proportional to log t to handle the boundary case. When t is equal to 1, then you need to add this additional 1 there. So you can bound this with 1 plus log t. Okay, that recovers the theorem after we divide both sides by this factor of 2. Okay. So the next thing that I wanted to do is to make use of this regret bound for the strongly convex case and show that this actually implies the improved convergence rate for stochastic subgradient methods. So recall in stochastic subgradient method, so this is stochastic gradient descent with stochastic gradient descent when the function is not necessarily differentiable, and the update rule is extremely easy. Is xt plus 1 is equal to xt minus learning rate eta t with the subgradient, with some approximation of the subgradient. So what we know is that the I guess the expectation of this gt given x is smaller than is equal to a valid subgradient. differential of f at xt. Okay, so this is the first assumption. The second assumption is that um, the variance uh, given xt is bounded. Okay, and then we also assume that this function f is convex and Lipschitz. Okay, G Lipschitz. Okay, so in our previous analysis, we showed that the stochastic subgradient method satisfies a convergence rate that is slow. We've shown that in order to converge to epsilon suboptimality, we need order of 1 over epsilon square iterations. Okay, so f x best expectation of this minus f star is smaller than order of 1 over square root of k after k iterations. Moreover, like remember that we've applied the definition of convexity and shows that you can actually average things out. And for the average version of the output, we can show that the expectation of f of xk bar minus f star satisfy the same. So all these are from lecture on subgradient, stochastic subgradient method. Okay, what we left with is a statement about the convergence of stochastic subgradient method in the strongly convex case. So we know that with additional assumption of M strong convexity, we can improve the convergence of stochastic subgradient method from 1 over square root of k to 1 over mk, where this O tilde captures all these polylogarithmic factors that's not polynomial in the parameters of the problem. Okay. And translating into the epsilon notation, and this means that for strongly convex problem, then we can actually get on the order of 1 over m epsilon iterations. So let's just make use of let's just make use of the regret bound that we learned today to actually recover all these results. Let's use the regret bound so that we can write this convergence bound as corollaries, including the case that we didn't prove under strong convexity. Okay. So following the algorithm, f so proof this. Okay, so following the stochastic subgradient algorithm that will output x bar k, so f of x bar is smaller than let's call it x bar t. So after t iterations, so this will be smaller than the 1 over t t from 1 to t f of x t. Right. So this is by the definition of convexity and in terms of Jensen's inequality. Okay, let's subtract star from both sides, then we get the suboptimality. And now let's apply the let's apply the linearization. Let's apply the definition of convexity again on this function f, which will give us 1 over t from 1 to t gt xt minus x star. Okay, so notice that we are basically we're basically doing the linearization at xt, okay, and then use it to lower bound fx star by applying the convexity and the definition of the subgradient. Okay, and now well, let's make use of the stochastic approximation assumption that this g tilde t is actually mean expectation gt. So let's replace that with okay. Since this everything is linear, we can exchange the order of this inner product with this expectation. So so we can extract it out and get t of sum of t from 1 to t, the expectation of the inner product gt tilde xt minus x star given xt. Now here, take a full expectation on both sides. Okay, so what are random here? So notice that in stochastic subgradient methods, this gt tilde are random. So so which the resulting iterates xt from x1, x2 all the way to xt. They're all random variables. So let's take the full expectation over everything, which gives us the this to be smaller than 1 over t, then the expectation of sum t from 1 to t g tilde t xt minus g tilde t x star. Okay. But notice that what we are seeing right now. So over this expectation, so for every sequence of realized playouts of all the possibilities of the subgradient methods, we can actually define ft to be g tilde t. We can define xt of x to be g tilde t inner product with x, right? So we can define xt to be like that. So with this definition, we can write it to be 1 over t, the expectation of sum of t from 1 to t, then ft of xt minus t from 1 to t, ft of x star. So I wanted to emphasize that this x star is the minimizer. Is a minimizer of f, of the original function f that we are trying to minimize with a stochastic subgradient descent. rather than not so x star is a minimizer of f, but not the minimizer of sum of ft, right? So but regardless, like if we look at the theorem of the regret bound, if we look at the definition of the regret, so we are defining the regret to be comparing to any u in the case. So we can always choose this u to be simply the x stars and minimizes that this original function that the subgradient method is minimized. Okay, so this is a regret. Point-wise, for every possible instance of this expectation, we can upper bound this regret with the regret of the OGD. And also check that the algorithm is running exactly OGD on this FT. Why is that the case? Since the gradient at xt, so the gradient of ft at xt is the same as the gradient of the original function f at xt. So therefore, we have this black box reduction to OGD that provided that we can bound the regret of OGD, then we get a convergence bound in the corresponding stochastic separating methods. Okay, so there are two cases. In the case of strongly convex, we know that the regret bound is 2m t log t, and there's additional parameter from the theorem. Let's take a look. So the additional parameter of the theorem is g squared. Okay, g squared. Okay, so what this is saying is that instead of having g squared, when we apply this, we actually have g squared plus sigma squared. Okay, and that gives the 1/t convergence rate of the strongly convex case. What if we plug in we plug in just the convex and Lipschitz function instead? Then the regret bound is square root of t gd 1.5 divided by t, which recovers the order 1 over square root of t regret convergence rate. Okay, so we have intentionally left this problem open on analyzing the stochastic subgradient methods for the strongly convex case because it is much easier to do the analysis when we use the reduction to no regret algorithms in the online learning setting. Okay, so we're almost towards the end of today's lecture. So I just wanted to make a few final remarks. So online convex optimization is a very general setting. So under this setting, so algorithms in this setting have strong implications in a lot of the interesting scenarios. Often those scenarios and these connections are not well known. Okay, so so specifically, we've talked about online learning. So in the last lecture, we talked about the batch learning. At the beginning, we talked about the statistical learning setting, where we observe data point z1 to zn from some distribution d, and then we wanted to find h from the hypothesis class such that H approaches the performance of H star in the sense that the expected loss of H given Z when new Z is drawn from some distribution comparing to Z drawn from the same distribution, the performance of H star is in some sense going to 0. So you can upper bound this with using statistical learning theory with things like 1 over square root of 1 over n. Okay, so it turns out that this batch learning setting also reduces to no regret minimization. So so I'm gonna I'm gonna leave the details to your homework, but this kind of technique is called online to batch conversion. So if you have a regret bound that's a sublinear, so that implies a statistical learning bound that's consistent, in some sense that goes to 0. Okay, so there's a homework question that's designed for you to understand this phenomena and understand the math in details in homework 4. All right, so that's the last thing I wanted to say today. Thanks all for coming. I guess I'll see you guys next Monday. All right, don't forget to submit the homework today.
Can I ask you one question?
Yes, please.
So when at the end of the strong convex case proof for OGD?
Well, this one.
Yeah. So at the end, there we have a harmonic series 1 plus up to 1 over t.
That's right.
Then you upper bound it by 1 plus log t, right?
That's right.
But we can also bound it by log t plus 1, right?
Log.
So t plus 1 inside of log.
Yeah. Possibly.
And that's tighter, I think.
Well. Suppose you choose t to be 1, then yeah, then maybe base 2 log. Yeah, suppose you use base 2 log, maybe you can get it.
Yeah, base 2. Yeah.
Yeah, I think that's right, and that's a good point. Yes, you can improve this with log base 2, like 1 plus t.
Okay, thank you.
All right, any other questions? All right, if not, I'll see you next Monday. Thanks all for coming.